Well, hello everyone. The other day on July 14th, 2010, that's yesterday in fact, front page of the Arizona Daily Star, big article dominating the front page was the fact that the Ames math scores had declined across the state. I read the article and it gave a web address that you could go to get more information. And I typed that in and it was the Department of Education. And as I was going through these links, I came across this one down here. Take the test, Ames. And so I clicked that open and followed a few other links. And sure enough, I got a PDF of a sample test with quite a few problems on it. And as I was skimming it, I came across this problem, which is right up the alley of what we're doing right now. And so I thought I'd give it a go. But before I do that, I just want to make a note here about um, for years I've resisted bringing in high school resources into community college Math 122, and the reason is because um, I've had students cheapen the course itself by saying it's just high school math. And yeah, that's true. I mean, a lot of the stuff we're learning here is taught in high school. But to lessen its force by saying it's just high school and cheapen it that way is not something I like to uh, give credence to. And there's a reason for that, and it's because this is actually significant math. And if you can do Math 122, you can do calculus. That I absolutely guarantee. Uh, Calculus is blown out of proportion in terms of difficulty. Math 122 that we're working on here actually has harder word problems than calculus does, for example. Now, all that being said, I'd also, having looked at this exam, this Ames test for graduating from high school, I would say that if we were to give it to the 60 state legislators up there in Phoenix and the 30 state senators and the governor, that is, if we were to give this exam to those 91 people, I would bet you that fewer than 10 could pass it. So I'm not going to pretend that this is not a difficult exam. You really have to study for it, and you really have to know your stuff to pass it. And all that's good. So let's get after studying and passing problem 25. Now it asks us what is the graph of the equation? And what I've done is I've rewritten it to make more sense to me, which is the graph of the equation. And here is the equation. It is a classic quadratic. And the reason why I'm picking on this particular problem here is it's very rich and will serve a lot of purposes here for us. For example, if you think about it, parabolas open down or open up. Now, they can also open to the left and to the right, and we'll be dealing with that situation in the next chapter. But for now, we're going to just think about plopping parabolas down that either open up or open down. And there's three situations that will occur if you do that. And this problem shows them all. The first situation here is where the parabola's legs cut the x-axis in two places. In other words, there's two x-intercepts where y is 0 and x is some numerical value here. And in this case, the quadratic equation right here, set to 0, will have two solutions. And that's why you've seen me repeat in many different places that most of the quadratics will have two situations. And then I would have a caveat where I said unless the solution is repeated. And that's the second solution, second idea here. The vertex of the parabola sits exactly on the x-axis, the vertex or the nose. And so the parabola only cuts the x-axis in one place. And this is a situation where we have what's called a repeated root. And it's actually the situation here. I don't want to spill the beans in the problem, but a heads up on that as I continue on here. The third situation is where neither the legs nor the vertex cut the x-axis at all. And if we were to set the equation that this is the graph of equal to 0, there would be no real solutions. And in fact, there would be two imaginary solutions. Now, in this particular flavor of 122, we're not going to deal with imaginary solutions. And so we won't have this situation. And that's because the people that built the course are sort of catering to calculus, which does not deal with imaginary numbers. Now, I wanted to get after this idea of opening up or opening down. It turns out that that's totally determined by the coefficient that sits in front of the x squared term. And so what I wanted to do was show that. There is the coefficient written with its numerical value and its sign. Now, if the coefficient is positive, then the parabola will open up. And so that's the case here in B and C. If this was a negative one, then the parabola would open down, like in A or D. Well, since this is a positive one, we know it's not opening down, and we can immediately exclude from this multiple choice Ames test these two answers. And we're left with either B or C. So that was the test for what's known as concavity. Is it concaved up or concaved down? And we found out it was concaved up. Now, I talked about the x-intercepts up here, and so actually what I wanted to do was sort of take a little divagation on this problem, if you will, sort of hack it. In other words, what I'm going to do here is I'm going to find the x-intercepts by setting y equal to 0. I want to find out if it's, which situation we're looking at here. If there are two solutions, two intercepts, one intercept, or 0 intercepts. And so I'm going to set y equal to 0 and solve that. And let's be very clear about what I'm doing here. I am letting y equals 0 to find the x-intercepts. Now, that's what we did when we were dealing with linear equations. To find the x-intercepts, we let y equal 0, and to find the y-intercepts, we let x equal to 0. That's true for any polynomial function. And so I'm setting y equal to 0 here to find the x-intercepts. Now, this is actually chasing back to an earlier section in the book where we first were introduced to quadratic equations, where we had a trinomial equal to 0 and the trinomial always cracked. And in fact, this one does crack into two halves like this. And if you remember, we used what was called the principle of zero products, and we said, okay, we've got two numbers here that multiply to give 0, either this one's 0 or this one's 0. Okay, what makes this number 0? And the answer was when x is equal to 2. And that's the same answer here. And that's why we say there's a multiplicity of roots. This is the situation where the nose of the vertex is right on the x-axis, and there is a redundancy of roots. And at this point in time, we've essentially answered this question. We were trying to find the x-intercepts. And so what we did was we said, well, we'll set y equal to 0 and we'll find out what x is. And we found out that it's a repeated root where x is equal to 2. And so this is a point on the graph. It is also the vertex. And if we come up here, 2 over and 0 up isn't even on this graph right here. And so we can exclude this one. And obviously the answer here is going to be graph B. Now, that is essentially sort of a hack of this problem. The way that you would probably solve it is the way it's taught in the book. And that is, what we would do is we would put the thing into what's called vertex form. And that looks like this. We would manipulate this and get it into vertex form. And it turns out to be pretty much the same path I followed here. What we would do is we would, if this was crackable, we would crack it. If not, we would complete the square on it. And since it is crackable, we could immediately crack it like this. And then I would write it in shorthand style. I wouldn't write both factors. I'd write it to the second power like this. And I would also show, since I'm aiming for vertex form here, I would write it as a square, and then I would show the k part off the rear here by showing I could always subtract 0. I'm not going to change anything to the left by doing that. And so this is vertex form. And when you have a parabola and a quadratic equation in vertex form, you can read off its stats. And the way you do that is you find out what makes this equal to 0, and the answer is when x is equal to 2. And then whatever y is equal to when this collapses is the y component of the vertex. So when x is equal to 2 here, this is all going to vanish and y is going to equal 0. And the vertex will be 2, 0, which is what we found by that other path that I took. Okay, so that's the Ames parabola problem. and I took sort of two paths to it, and we got to cover some interesting issues regarding parabolas and the x-axis. I hope it helps. I'll be talking to you soon.